Thank you. Good afternoon, everyone. I'm glad to be here to discuss uh, some of my recent research and some thoughts about symbolism. Okay. My report is outlined as follows. First, we will briefly overview two methodology in AI, that is connectionism, and symbolism. Next, we will discuss the historical symbolic AI events, talk about the rise of symbolic AI and the failure of symbolic AI. And last, we will talk about why we need the return of symbolic AI. Okay, first, the connectionism. The connectionism involves using neural network that mimics the structure and function of biological neurons. Everyone knows that about the neural network, right? It's with distributed representational knowledge, learning through adjustment of weights in a network based on data, and ability to generalize and adapt to new inputs. On the contrary, the second paradigm of AI is symbolism. It focuses on using formal symbols and logic to represent knowledge and perform reasoning. The characteristics as follows. The knowledge is explicitly encoded in symbol and rules, and the reasoning is often rule-based. The reasoning is often rule-based and deductive. The systems are interpretable and can provide clear reasoning paths. Let's see a brief history comparison between these two paradigms. From the historical view, it shows the ratio of maybe the influence of connectionism, and the logic symbolism. We can see from the birth of AI and to the 1960s, the connectionism have more influence than symbolic AI, right? Because of the perception. But at this time, the Misty's perception, published at 1969, destroyed the connectionism. And since then, the symbolism dominates AI for maybe a decade. But again, in the maybe 1995, AI winter occurred, and the symbolic AI is done. And the machine learning and the big data and data-driven method rise up. And it goes today until the LLM dominates everything. So this is a brief history of these two paradigms in the history of AI. Okay, let's focus on the history of symbolism, the rise of symbolism, why people need them. First, the symbolism is the earliest school of thought in AI. Its core idea is that the essence of intelligence lies in the logical manipulation of symbols, that is, simulating human cognition through formal rule-based systems such as logic, mathematics, grammar, etc. And this is the belief of founding fathers of AI. These guys, everyone know them, right? Turing, Alan Newell, Herbert Simon, John McCarthy, and Marvin Minsky. Let's see them one by one. Turing, although he did not directly engage in symbolic AI research, his proposed Turing machine model lays the theoretical foundation for symbolism, right? Turing believes that the machine could simulate humans through human thought through symbolic operations, which align with the core idea of symbolism. And Alan Newell and Herbert Simon, they are strong supporters for the symbolism. They propose the physical symbol system hypothesis. This is a very strong hypothesis, arguing that any system capable of exhibiting general intelligence must be a physical system capable of manipulating symbols. And they developed two famous systems to verify this hypothesis. And they firmly believe that the symbolism is the only path to strong artificial intelligence, asserting that all cognitive activity can be broken down into rule-based combination of symbols. We will look back to this hypothesis later. And then Minsky, he believed that the intelligence requires a hierarchical symbol structure, emphasizing knowledge interpretation and frame theory. And his book, Perception, destroyed the connectionism at that time. And his attitude is somewhat flexible. He supported symbolism, but also believed that other approaches, such as connectionism, should be combined to address issues related to perception and intuition. Then McCarthy, he believes that symbolism is the foundation of building general artificial intelligence, advocating for the new use of formal logic to express knowledge and reasoning. He eventually leaves this programming language and he proposed a logical AI and promoted the development of expert system. And he believed that the symbolic system could achieve human-level abstraction thinking through logical rules, but he was also nearly aware of the limitation of symbolism. Okay, this is the view of the founding father of AI. Okay, let's review the strongest hypothesis about the symbolic AI. That is the physical symbol system hypothesis. And symbolic system is both a necessary and a sufficient condition for achieving intelligence. First, a system capable of generating intelligence must be a physical symbol system. And conversely, any sufficiently powerful physical symbol system can be programmed to achieve general intelligence. So it's a very strong. Let's see them in detail. Okay, first, the intelligence is equal to symbol manipulation. Our cognitive behavior reduced to rule-based processing of symbols. For example, math, right? Math manipulate numbers and operators. Second, universality. A sufficient powerful symbol system can simulate any intelligent behavior. This is analogous to the universality of Turing machine. And the computability. Symbolic operator can be algorithmically implemented, meaning intelligence can be programmed and replicated on computers. This is a physical symbol system hypothesis. This is the foundation of the symbolic AI. Then people began to implement system to verify whether this hypothesis is correct. So they built a lot of famous systems in that area. Let's see some of them. First, in 1956, Newell and Simon developed the logical theorist. This is the first demonstration of how symbolic system can simulate human reasoning. This makes the birth of symbolic school. It can prove 38 theorems from the principal Mathematica, and even proposed more concise proof method. This is start of symbolic AI. And next, also these guys developed the general problem solver. General problem solver, this name is just another name of AGI, right? General problem solver. And it was applied to classic problems like the Tower of Hanoi, demonstrating that the symbolic system can handle structured problem. Then the symbolic AI goes to its golden age, that is the expert system, inspired by the famous Edward Feigenbaum. He wins the Turing Award in 1994 for his pioneer work in AI, especially in expert system. And he built this expert system, first danger in the domain of chemical mass spectrometry analysis. It uses rule-based reasoning to identify molecular structure of unknown organic compound. And he combined chemical expert knowledge based on heuristic search algorithm, achieved or even surpassed the accuracy of human expert in experiments. Then he built the Mingming. This is the most famous AI system for symbolic AI. Right? Mingming is in the medical diagnosis field and use the production rule and introduce the uncertainty reasoning. And he achieved the diagnostic accuracy comparable to top doctors, become a milestone in medical AI. And next is a commercial system, means the symbolic AI to not necessarily stay on laboratories, it can apply it in real world. So in 1917, the DEC developed the XCOM R1 system to help people to make computer hardware configuration. It saved DEC $25 million annually and reduced the error rate from 30% to 2%. So this is the first largest scale commercial expert system. This demonstrates the practical economic value of symbolic AI. So this is the typical system of the golden age of symbolic AI. But after that, the failure of symbolism is coming. Why symbolism failed? Let's just go to the failures. First, again, XCOM system. Previously, a successful system failed in the next few years. The reason is that the system needs high knowledge maintenance cost because the hardware configuration changes timely, right? So each change requires manual intervention. And if you want to adapt this system to other field, and it costs a lot, and you almost need to rewrite the whole system. So in the 1990s, when DEC was bankrupt and XCOM was discontinued. And in the 1993, the US AI industry market shrunk by 30%, leading to what is known as the AI winter, because of the failure of the expert system. And in the other direction, the failure of common sense engineering, the CYC project. The CYC project is to build a knowledge base covering human common sense, like the bird can fly, and the grass cups are fragile. At that time, people think the project may also fail because although it is continued today, still continued today. But at that time, after 40 years and over 25 million annual manually entered logical associations, the complexity of common sense are still far from being covered. And it cannot handle exception. For example, the penguins are birds but cannot fly, and a context-dependent situation, water is drinkable versus the floods are dangerous. So the lesson from the CYC is that common sense can be realized through exhaustive rule system as a closed system. Okay, the most famous failure is Japan's fifth generation of computer project in 1980s. The Japan's fifth generation computer project is very ambitious. They want to build an intelligent computer based on Prolog and symbolic logic to lead the goal of AI field, global AI field. The reason of failure is that they rely on over-reliance on symbolic reasoning, neglecting other capabilities such as perception and learning, and mismatch between hardware and algorithm. The parallel reasoning mechanism was difficult to implement, and Prolog's efficiency was inadequate at that time. Still, at this time, Prolog is very slow. So the result of this project is with a decade-long investment of $850 million. The result was almost negligible, severely damages the international reputation of symbolic AI. Okay, so with these failures, what can we learn? Why symbolic AI fails? First, the theoretical defeats of symbolic school is that the knowledge acquisition bottleneck. At that time, the knowledge of symbolic AI depends on manual encoding, making it very difficult to automatically learn from data at that time. The second is the inability to handle uncertainty. It only supports binary logic at that time, making it impossible to handle probability, making it a partial truth. For example, in autonomous driving real-time decision, like a pedestrian suddenly appears, requires a car make a probabilistic reasoning. But at that time, the symbolic system cannot address this problem. Okay, and the key problem, one of the key problems is combinatorial explosion. The search space of symbolic reasoning grows exponentially with the size of problem. This is a major problem of symbolic AI. For example, the automatic theory prover only works up to 10 steps, but when you go to 100 steps, the procedure becomes uncontrollable. This is still a major problem in symbolic AI. Last, the lack of common sense and contextual understanding. So symbolic system requires a knowledge base, right? But some implicit knowledge, for example, a cup overtuned wheel, will spill water requires physical common sense. This knowledge may not reside in their knowledge base. So this is a very important problem, critical problem for symbolic AI. And finally, because of these limitations and the external shocks and paradigm shift, the symbolic AI is discarded. First, when the time goes to 1990 and 2000 year, the big data and computational power revolution comes. But symbolic AI cannot take advantage of massive amounts of unstructured data available to the internet, right? And second is the rise of connectionism. For example, in 2012, AlexNet wins the ImageNet recognition competition with large margin, and the deep learning become mainstream. And the enterprise also abandoned the development circle, high cost, and no real-time decision. So it is also not work well in real world system. At this time, the LLM dominates almost everything, and the only remnant of symbolism is knowledge graph. The knowledge graph live to today because it is application driven. For example, it is proposed by Google in his search engine product. It's focused on specific domain task products. It simplifies the knowledge expression just to use triplets. It naturally integrates machine learning techniques for knowledge acquisition and maintenance. And it is able to handle ambiguity and uncertainty. And it employs simplified reasoning method. For example, the embedding-based reasoning. So knowledge graph is a combination of symbolism and connectionism. It is a much simplified symbolism system. But this is a typical knowledge graph. This is a typical knowledge graph, including the entity of the word and the relationship between them. And this is Google's product using that knowledge graph to generate precise results for the query, like the place to visit in Los Angeles. Okay, even the knowledge graph is the only remnant of symbolism. The usefulness of the value of knowledge graph is also being challenging today. But today we are talking about the return of symbolism, right? Why we are talking about this? Do we really need the return of symbolism? I think so, because strange things continue to occur in LM world. For example, most people know that months ago, the problem of which one is bigger, 9.11 or the 9.9, almost all the LM give the wrong answer, and in this situation, it insists it's wrong answer and do mistake math about this problem. Today, the problem is fixed, and almost all LM give the correct answer. But this one is the case I just made this slide. How many fingers are there? It's actually 1 thumb and 5 other fingers, but they told me there is only 1 finger and 4 other fingers. So why is this? There is recently a paper analyzes this problem. They make a lot of confusing pictures and input it to the LM, let them to answer the question. Almost all LM fail to answer the correct answer. All of them tend to give the most normal answer of the similar picture. For example, this picture, the chicken has 3 legs, right? But almost all of them return 2, and one of them return 4. And this is a 5-circle brand on your car. And this is a 3-circle, or 3 or 5, I don't remember. And this is a flag with 14 star in the US flag. And all of them are wrong. So the conclusion is that in this case, LM do not really understand, they memorize. And we will talk this phenomenon later. And due to these cases, they may occur at every time you use LM. There is almost no rules where when this error will happen, right? Most anyone makes these mistakes for wrong computation, false reference, like something like that. So people are worried about LM's hallucination, and there are some reports about the damage of hallucination. For example, in 2024, the global economic losses caused by the hallucination is 67 billion. And according to the first research, each company will cost $40,000 per employee to cope with the hallucination phenomenon, including manual verification and error correction. Hallucination is very widely existed in LMs. This is the most recent evaluation of LM. And for example, for the legal domain, where people need the precise information most, the hallucination rate is about 6%. So it's a big challenge to human society. And someone worried about this, about the false information spreading on the web. So they built a website called Low Background Still. This website stores all the web pages generated before the generating AI is popular over the world. So almost before the 1222, year of 1222. And the low background still, this name comes from the fact that after the nuclear bomb exploded at 1945, all the new created steel naturally contains the nuclear pollution. Only those built before the 1964 is clean of this pollution. So the worries about LM is spreading. So, but what is the hallucination of LM? Is a bug or feature, or can we eliminate it completely from the LM structure, pure LM structure that no other no other mechanism? The answer is no. There is an intrinsic confliction of generalization and memorization. The machine learning models learn things with decreasing frequency. It is related to the model capacity. If the model capacity is excessively large, the continuous learning finally will result the model into the situation that it memorizes everything, including mistakes, so no generalize. So we must use a smaller model to fit the data. This is called in the field of AI, that is compression generates intelligence, right? But if the model is limited, it will first learn the pattern. This is called generalization. Why this is learned? Because the pattern is the most frequent thing in the data set. The next is the high frequency facts. But finally, you will lack sufficient model capacity. Finally, you will lack sufficient model capacity for low frequency facts, and thus hallucination occurs. So next, there is another limitation of LLM. It do not differentiate the real facts and the induced guesses. In the symbolism, if a fact is in the knowledge base, you know it's correct with high confidence, right? And the induced inferred knowledge from the inference engine, you know it is maybe problematic and need to check. But LLMs memorize real facts from training data and infer or induce new information in their training procedure or the inference procedure. They cannot differentiate the facts versus the inference. They all the computation between the inner embedding vectors, right? And there is no verification token generation. So they will lead to cascading error. This is why LLM's hallucination is difficult to solve. People try to use LLM everywhere, so they make efforts to lower down the hallucination. The first is to use external knowledge, which is usually called RAG in LLM field. The basic RAG pipeline is that if you have a confidential documents, that you can assure that the LLM definitely do not ever seen it. So the LLM definitely cannot answer the question correctly. So you can build your confidential documents into a vector-based knowledge base that you split the document into chunks and make its embedding its trunk into a vector. And when the user query is coming, you match the query with embedding. You match the query embedding with the document embedding, so the relevant text trunk will be retrieved. And you combine these trunks as a background information and put them into LLM together with the user query. LLM will use the background information you provided and give the correct answer. But there is a problem. How the data the quality of your data. Is there any popular or public available and robust method to evaluate whether the information in your document is correct? There is no such system right now. Okay. The second effort is result verification. This is this sort is very straightforward. In some domain, like the code or math, you can run external tools to verify the generated result. Right? For code, you can run the compiler, or even construct an auto test unit to test the correctness of the code. But generally, we do not have such information. So there is a strategy called self-consistency. That is, you just let LLM to generate several candidate answers and make a vote. This is self-consistency in some situation. Indeed, improve the accuracy of the LLM, and it can be used to further fine-tune the LLM. This results in the last major efforts, reasoning. Although LLM is proposed firstly to directly output the answer in the end-to-end way, but in the chain of thought in 2022, in the year of 2022, chain of thought brings LLM to a new phase, that is implicit symbolic reasoning. LLM have this capability. It can, based on the input and the step to do the operations to get the final result. Using this implicit symbol reasoning, it does not use memorized final results. It uses operation, calculation, and step to make the final result. So the performance is much higher. And more importantly, when the high quality result verification is available, we can train LLM to learn to reason. This is a completely different scenario for LLM. The most typical system is OpenAI's O1 and DeepSeek's R1. The DeepSeek R1 use a set of problems with ground truth answer, majorly from the math or code, or maybe have some single selection problem like that, and that's LLM to solve it. And it asks LLM to first think about the problem and think how to solve them, and write down the procedure of solve them, and then to generate a result. When the result is generated, they extract the result and compare to the ground truth and make a reward to the learning procedure. Using this reward and reinforcement learning procedure, we can see this from this graph. At the beginning, the model almost not thinking. The length of thinking is very, very low, maybe 0 or 1 token like that. But when the training continues, the thinking is more and more. Machine learns to think, and finally, they build a powerful model. The capability of this model is not limited to the domain of the training data. The training data is in the math or code, right? the capability of this model does work well on these domains, but this thinking ability generalized to other domains. Other domains' performance is also improved. So currently, LLM can do some reason. And there is a typical case to gather all this information together. Let's look at it. Case study, retrieval augmented math prover. This system does the math proving step by step. First, it put the current step into a retriever, and the retriever will find the most possible useful theorems from the MathLib database. And then they put this step and together with possible useful theorems into a prover to generate next step proof. And the next step proof is to pass it to a verify to find the correct next answer, including whether this statement, the format is correct or it is really can be induced, deducted by the previous theorem. The theorem after verified by this verifier is then put back to the proving process, and until at the end, the proving is end, the theorem may be added to the knowledge base for future proving. Okay, this is the most modern LLM system. It is for math prover, but if you want to make LLM work in real problem, you always need something like knowledge base, and you always need a verify to check the final results. Okay. So given this system architecture, the symbolic guys may find it is very similar to the symbolic system. The knowledge-based system is just like that. It has a knowledge base. It has a TMS, the truth maintenance system. It verifies the output of inference engine and put it, if passed, put it into the knowledge base. And there is an inference engine to do reasoning. So the paradigm of symbolism is back, although it is not using the name of symbolics, right? It's called RAG. It's called verification or self-consistency. But this system is just identical to those of the knowledge-based system. Why is that? Because if you want to solve a real-world problem, there are common must-solve problems for any AI paradigm. Whatever you are the cognitism guy or symbolism guy, you also faces this problem. High quality knowledge is needed, and the ground truth verification is needed, and a fast, reliable reasoning engine is needed. Currently, we actually have this one, largely addressed by reasoning LLM. We can do a lot of things that cannot done before, but this tool only still constrained to limited domains, example for code and math. If we want to spread this paradigm into a general purpose situation, because we want AGI, right? We are facing this two problems: high quality world knowledge and efficient truth verification over a large scale KB. Okay, again, fundamental problems of symbolism resurfaces. These problems are faced by those symbolists maybe 40 years ago. We are still facing this problem today. So the shadow of symbolism past failures remains here. Okay. So why is that? Why this problem is not solved? There's a lot of think about this problem, but I think the most important one is this. Proposed by Rich Sutton. His article, The Beta Lesson, he summarized 70 years of history of AI development, and he concludes that AI researchers have often tried to build knowledge into their agents. This always helps in the short term and is personally satisfying to the researcher. But in the long run, it plateaus and even inhibits further progress. Breakthrough progress eventually arises by opposing approaches based on scaling computation by search and learning. Okay, this is a big strike on the current state of previous two problems. This one. Why this problem is still not solved? Because we do not reach the status of scaling computation in symbolic AI. So this is the most critical problem about the symbolism. It is they never achieved scaling computation. First, symbolism never reached the big data stage. KB are limited to triples, missing rich world information. And the KBs are isolated and lacking operability. We'll see this case later, why they are isolated. And second is the problem that symbolic inference, for example, Markov logic network, is of high complexity, blocking the scalability. So to solve the problem, we may need to a new symbolism, a new connectionism. In the new symbolism, we need from extracting partial data to representing the full data. We need more data to the big data stage, right? And we need from the task-specific data to general natural schema. We want general AI ability, not limited to a specific domain, right? And we need fast reasoning on Markov logic network. Accordingly, if we build this new symbolism, we may require the connectionism system do their decision or inference from token space to knowledge space. So this is a new symbolism and new connectionism combination. Now let's focus on the new symbolism. An important question is that, do this really necessary to consider this problem when the GPT-5 is approaching, right? Everyone now knows GPT-5 is approaching. And it may be a very, very another revolution on this LM field. And many problems may be solved by GPT-5, and we are still talking about this. Is it necessary? I think so. The new symbolism is not merely a tool to enhance the performance of LM. A deeper understanding of what knowledge holds intrinsic value is intrinsic value, independent of task completion by LM. For instance, truth verification and maintenance system are closely tied to the shared consensus of human society. Something that remains implicitly embedded within LM's value alignment. Every company align their model with their own value, right? People all know discussing about the groks implementing the masks value, right? And every LM implementing their own value. But they are also, all hidden in the LMs. Bringing this issue to the surface benefits not only AI development, but also foster deeper reflection and progress for humanity itself. So it's still unnecessary. Okay, the time limits we will go through quickly. Next pages. Okay, but now we talk about what we do to go to the new symbolism paradigm. First, from the small partial data to big full data. This is a workflow of current KB. To build a KB, you need first a schema, define a symbolic schema, and means you focus on this type of information. And when you extract knowledge from data, you just detect the entities from data and decide whether this entity has relations. If they have, you mark these two entities have a symbolic relation, and then discard all other information. They discard all other information. So this is a very, very, very serious problem for the object to make big data. Because we always discard most information just to accomplish a simple task. So to overcome this scenario, we find that lingual graph, general representation, and the free schema. We pass the sentence into a graph, and people concerned information, entities, relations, and open relations all can embedded in this graph as a graph learning task. You can add a link to represent the information relationship between this entity. You can open a relation is a subgraph of this structure. So with this structure, the information is kept, and it is a hierarchical structure of predicates, function, and arguments. So it's a structure. It's knowledge-oriented structure parser. It's schema-free, general proposed, and oriented towards knowledge representation. And it's a high bandwidth pathway from language to knowledge. So this is our recent work to put the knowledge from small partial data to big data. Second, from the big data to scaling computing. If we have a large-scale knowledge graph, we always want to do some inference over this knowledge graph. The most suitable model is Markov logical network. The words are defined by set of constant facts and rules, and the Markov logical network assign probabilities to each possible word, learns this probability from data, and perform inference over them. This is a rule defined in the word, and the facts is about friends, smokes, and cancer, and the constants is ABC. With this information, a Markov network can be constructed, and you can do inference over this graph. And the first work we do, okay, this is a theoretical model of Markov logical networks. The probability of this word can be explicitly written, and the learning is about the weight of the rules in this word, and we can inference. If we have learned this model, we can inference the probability of a formula in this word, the probability of the truth of a formula in this word. And the first work is the fast ML learning and reasoning. This work also have been presented by Professor Cai, because we previously are working together to make this work. It's ML for KB. You already know that. And the second work is Embedding with the PSL, and Professor Tsai also represented this in the formal talk. So I skip this. And there are still many open problems for the new symbolism, and we are working to solve them one by one. For example, reasoning over natural schemas with super large scale knowledge is an open problem, and updating and maintaining consistency in large scale knowledge system, and modeling truth across diverse historical, educational, and the ideological contexts is a very challenging problem. And interfacing new symbolic paradigm with connectionist architecture. And last, if we have this large-scale knowledge graph, can we generate a novel concept to drive discovery? All these problems are very interesting for the new symbolism. Okay, finally, let's summarize this talk. First, the return of symbolism is inspired that the connectivism increasingly demand high quality word knowledge and rigorous verification. Yet its inherent limitation and make this challenge difficult to solve. Historically, symbolic approaches were the first to model and address these problems, but they ultimately failed due to a lack of computational scalability. Today, powerful large language models have greatly enhanced our ability to process linguistic and cognitive signals, making scalable symbolic computation possible. This evolution mirrors how complex cognitive structure emerges in a mature brain through natural evolution process. That is, a higher intelligence of human is occurred after the perception ability of general animal, right? With such ability, we can develop more higher level of cognitive structure. So finally, a fully developed connectionist machine results in a better symbolic system. The fully developed symbolic system in turn results in a better connectionism machine. This is a round and up procedure. At last, let's review the history of symbolism and connectionism. It is noticeable that the most fundamental breakthrough of connectionism occurs at the time when the symbolism dominates AI, the BP algorithm, and the convolutional network. So maybe it's time for us to do research on symbolism. Okay. Thank you. That's my report. Any questions? Yeah, sure. The combination of symbolic AI, including the math equation, human knowledge into a neural network, is a mainstream study direction these days, right? But if we can make further, a portion of knowledge can symbolically embedded to the LM or neural network is relatively low today. We can make them more and more and more and make a better AI system. Yeah, yeah, yeah.谢谢。